Thank you. Oh, beautiful. Thank you, Kayla. Nice. All right, welcome to Real Analysis, friends. This is probably the last time I'm going to be teaching this for a little while. Usually do like 3 years of these upper level classes. Dr. Seibert takes over next time. And we're pretty much the only two who teach this class, it seems like, because we freaking love it. It's like the best class that we offer. Let me take off my shoes. No offense to all other math classes, but this is the shit. So in all my classes, I usually start off with a little mindfulness, just to kind of do a reset, get our palettes cleaned, our mental palettes, and to give you a chance to actually just have a few moments where you're not trying to process mental information. So you can join in. It'll only take a couple of minutes. You don't have to. All I ask is that you kindly sit quietly, as opposed to making weird sounds or anything like that. So, we'll talk more about this as we go along. Just kind of get comfortable and feel your seat. Take note of the pressure of your body on your chair. You can close your eyes for this. Sometimes we'll have our eyes open. Let's just close them for right now. Doing a quick scan from top to bottom. Starting at the top of your head, just noticing what that feels like at the top. Slowly progressing down through your face. Feeling your face. Feeling the back of your head. Down through your neck. Letting your shoulders relax as you notice. Probably some tension being held there. Continuing on down, just your arms, hands, your torso into the picture. Back down to that contact with the chair. Legs. Lastly, noticing what your feet feel like. Seeing if all at once you can bring all of those sensations in as a single sensation. Just feeling the buzz in your body. Nice, all right. So, my friends, let's see, we've got some business to take care of. The syllabus is up online. Does anybody read syllabi? It's like, I know, it's like, I mean, we spend hours writing these things, you know, and some of them are voluminous. You know, anybody ever had like a class with Dr. Patnott? I think her syllabi are like tomes. It could be published. Mine are kind of like that, but it's a lot of boilerplate that I just cut and paste from the original syllabus many, many years ago. And here's the key things. This class is primarily homework. We will probably have around 10 to 12 homework assignments. Those will constitute 60% of your grade. And homework is really important to me. It's in fact so important that I put a little sample up online. If you've never had a class with me, I'm a really big stickler on homework quality. And some of you I know produce fantastic homework. I know at least three of you, I know you all three produce beautiful homework. I don't know your homework, but I imagine it's incredible. And if you're curious, like what is he looking for, there's a little sample. And the sample is mostly an anti-example of what I'm not looking for, what I don't want to see. So if you need help with that, just go for it. One thing is I do want problem statements on every piece of homework. Doesn't have to be verbatim, but I want it so that if someone picked up your homework, they would know what you were solving. Occasionally that person will be you. If you want to pick up your homework and go, what the hell was I doing here? Just a little, you know, what's about to happen. Let's see, so syllabus online, homework quality, cool. I'll just say this. I'm not actually concerned about it at all. Even folks I don't know, I feel a sense that this isn't a problem. But every real analysis problem in the world has been worked and is published online somewhere. I know what a lot of those solutions look like. You're gonna just be so much better off if you just struggle, and especially if you're like, I can't get this problem, that's cool, do your best. That's what I want, just effort of your own quality, and you know, we'll work it out if things go really awry. I'll give you chances to make that up. Trying and effort and high quality homework gonna get you through this class. Yeah, I guess we'll have 2 exams also. We'll have a midterm and a final. I think our final was like Wednesday at 8 a.m. We're not doing that. We're not doing that. Our exams will be take home. They'll essentially be take home exams, and I'll give you ample time, and we'll work on them in class. And also, if you've had a class with me before, this is pretty standard. Okay, so if you have not yet, and it looks like everybody had logged into the class. I was super stoked to see this. Please read sections 1.1 and 1.2, but for Wednesday, move up to 1.3. So if you've actually already done the reading that I recommended earlier, you're in good shape. Read up through 1.3 for Wednesday. You're probably always going to want to read ahead in this class. The concepts are heavy, and they come fast. And even the simplest things, like we're going to talk about today, are really deep and incredibly useful. There's going to be 3 things today you're going to see over and over and over again in this class. And you've already read them if you've read through that first section, 1.1 and 1.2. Okay, we have a homework assignment. It's up online, but I'll pop it up on the board for you in case you like to put these things in your notes. I add these things to the calendar. This is due Jan 21st. So due 1/21. And this is 1, 2, 3, just A and B. 1, 2, 5, A and B. 1, 2, 7, 1, 2, 8, 1, 2, 12. This is in some sense a review assignment. So some of this is, do you remember how to do induction? For example, this one is, do you know how to do induction? What would be really cool is if you could at least just read these through by Wednesday, and then we can talk about it. I always want to talk about homework. I always want questions. What does this mean? How do we get started? That would be great to talk about on Wednesday. I think this is next Friday, a week from this coming Friday, something like that. So we've got plenty of time. Alrighty, what is this class about? Real analysis, right? Let's put this up here. This was essentially the focus of my PhD work. My PhD work actually took place in something that's called functional analysis, which is essentially an infinite dimensional version of what we're going to do in this class. This is a 1D class. We study a line the whole semester. We study the real number line. And we denote that with an I. So that's the real number line. Doesn't look like it could be terribly complicated, but oh man, hundreds of years worth of exploration have been done here. And we're going to kind of hit the highlights of those. So in this line, this line is made up of points. This is a one-dimensional object. Points are zero-dimensional objects. We may or may not get into that at some point. Kind of feel like we might, but not right now. Inside here, there are some other sets that you're well acquainted with. So let's talk about the number subsets of the real line. So the first one is the natural numbers. And this is the first numbers that humans ever conceived of. This is the how many freaking sheep do I have, right? How many bones are in my bone pile in the back of my cave? This is the counting numbers. So this is just the natural numbers, which are just 1, 2, 3, on up. You can think of that as the positive integers. The whole numbers include 0. And as soon as 0 gets in there, we're starting to head into the land of the mystical, right? Like even there's some mysticism here if you're really interested in it. But as soon as we toss in a 0, now you know the first time 0 was written, somebody probably got killed for writing it and thinking about it, because you know people just getting upset about shit. So as soon as you add in 0, you get this thing called the whole numbers. I don't know, I'll try to do that's weird. I don't know how to do a Gothic like W. That's supposed to be a W for the whole numbers. It was spelled with a W, not an HOLE, even though 0 is kind of a whole. Then when we extend this out into even more mystical things and more abstract things, we can add all the negatives of these and we get the integers. So that's Z. And that is the plus minus version of all these, including 0. So we can write that in a nice way. So you could also write that as a doubly infinite set, if you wanted to do that. You just indicate that to the left this continues, and to the right this continues as well. So looking at this number line, what do these sets look like? Well, let's just start with the integers. We've got a 0, and that's a point. And we've got 1, 2, 3, minus 1, minus 2. Not to scale. I feel like my scale's a little wanky there. Wonky, funky, off, but you got the point. The Greeks loved the integers. They loved whole things, but then they also loved ratios of whole things. This commensurate quantities was something that Euclid talked about. Well, one of the most famous Greeks, right? And we do a lot of work thanks to Euclid, who's the developer of proofs. First textbook was a math book. We are a proud people, us math peoples. So when I start taking ratios of whole quantities, allowing pluses and minuses, I get the rational numbers. So I've got ratios of A to B, where B is non-zero, and A and B are integers. Now let me stop for a second. Is this notation okay with everybody? This is just an element of, if you ever want me to explain something, please, let's do that right up front. So let's come back to the line.
if I wanted to start putting dots for all these things, we're going to end up in a world of hurt. And one of the great studies of this class are the rational numbers. And how do they sit? How do the rational numbers relate to this line? How do they relate to each other? The best you could probably do if you wanted to indicate these would just be a hazy cloud. And that's not even hazy enough. But the rational numbers just form, let's put a 0 in there, that's one of them. Just form a cloud subset of these reals. And the nature of that cloud is something that, again, we will study. If I fill in these holes, what kind of numbers are left, actually? The irrationals, right? So anything that can't be written as a fraction. When I add those in, I'm going to call those I with a capital I. So this is equal to the irrationals. And it's equal to, check out this notation, this is kind of cheesing out in a little way. I'm going to say it's all the reals minus, this is a set minus. You might not have seen it written like this. You could also write it as a horizontal minus, totally kosher. You don't want to do it like this, because then you're getting into the realm of abstract algebra and modular groups. And you know, we don't want to go, we're not going there in this class. That's a whole other semester. So we say minus Q. It's everything that's not rational. Turns out, if I sketch these, they are also a cloud. But the cloud turns out to be a lot heavier. So this is a cloud for Q. This is a heavier cloud. What the hell does he mean by that? Well, we'll get into it. There's way more of those things than there are the rationals. Way more. When I put these two things together, Q and I get our buddy for the semester, the real numbers. Beyond that, there are more numbers. In a recent development is something called the surreal numbers. You ever heard of these? So the surreal numbers were invented, discovered, who knows what that is in math, you know? Not sure which is which. By John Conway, famous mathematician, and David Knuth, who's written a lot of computer books. He's kind of a computer guy. But there are these things called the surreal numbers, which are a superset of the real. So I'm going to say they contain, that's a containment. They contain the reals. Essentially, it's the reals, and you add in all infinitesimals. And an infinitesimal is a number that's smaller than any other real number. So they're like dust. And this idea came from Leibniz, back when Newton and Leibniz were racing to develop calculus. Leibniz had this whole idea of infinitesimals, quantities so small they were smaller than any other number. And so they formed this little cloud around 0. We don't use that. You could do calculus that way if you wanted. It's called non-standard analysis. We don't do that here. Most people don't do that ever. They're kind of weird dudes, dudettes, peoples who do all that. So you add in the infinitesimals and the infinite, let me see, wait, there's the exact term for it. Infinite ordinals, yeah. So then you're allowed these infinities. Infinite ordinals. So these are just a collection of infinities. And we will study those. We will study. This class, to me, is all about infinity. Big infinities, little infinities. So you toss those in, you get the surreal numbers. Beyond that, there's some you know, there's some that I know one of you knows quite well. That is the complex numbers. where we toss in the imaginaries. So this is complex numbers. This is also a superset of the reals. This is all things a plus bi, where I is the square root of -1. You can have a whole semester's worth of fun. And you should. Turns out that class, despite the name complex versus real, that class is much easier than this class. Despite the name kind of throwing you the other way. And then beyond the complex, there's some things called the Hamiltonians, where you have a plus bi plus cj plus dk, and these ij's and k's act like imaginary quantities. This is like physicist stuff. We're not going there. And then there's actually some more beyond that, fancier number systems. There's a lot of numbers. There's a lot of numbers in the world. Or they're just in our heads, one of the two. Really doesn't matter. We're going to study them anyway. Okay, so friends, how many folks actually have gotten a book yet? Okay, cool. There's the PDF up online, so you definitely have enough. I'll put up 1, 2, 3 as well, so that you have that accessible. If you get a book, I would like you to bring it. Please, it's a small book and it's easy to carry around, but we're often going to refer to things so that it just doesn't get pedantic and I'm like just reading you stuff from the book. That can get really boring. But one of the first things I wanted to talk about today beyond this is example 122. This is a pivotal example. Now, I'm like put stars all over this because you are going to come back to the concept of this example almost every week. Time and time again, we will come back to example 122 in the book. So let's just take a look at it together. Star. And the key thing here is the idea of what's about to happen. So let's get our setup here. We create a sequence of sets. And our first set is just the naturals. We start there. That's A1. A2 is going to be the naturals minus the 1. So it's actually just kind of scooting over just a little bit. So this is going to be 2, 3, 4, on up. You probably get the rhythm, but let's make sure. Because you're never quite sure. You need at least like 3 things usually to tell if there's like a pattern and verify it. And then if I were to generalize this, and I know you guys split at some point, but yeah. I'll have that recording up later today.
Thank you.
Good to see you. This is going to start at n plus 1, n plus 2, and so on. So, let's talk about some set operations with these things. All right, so first off, let's talk about the union of all these sets. What would that be?
Union is just all unique elements of each set, right? It's not all, like I don't have 2 twice.
Correct, yeah, so, yeah, if I union these two, each element is only still represented by 1 thing, yes. So what do we think that, does this union make sense? Let's, let me make sure. So you can think of that as the smallest set that contains all of those sets. That's another way to think. We can write that let set be? Any ideas? Yeah, it's okay, we can be wrong too, it's like, just us.
Wouldn't it be A1?
Yeah, why is that?
Because A1 is the only one that contains all of the elements.
Sounds
That
about
would
right,
forever be-
yeah, absolutely, yeah, right on, Kayla. So the answer here is, this is just A1. You might want to get used to drawing pictures in this class. So let's just draw some pictures. A1, and this is a simple example, right? And sometimes drawing is going to be impossible. But here's A1. Underneath that, I'm going to put A2, and we might want this for the next question. Let's just do one more. And so, and I could even do a general representation of A sub n, which is going to look like this. Let's see, here's 1, 2, 3, and then I put ellipses, n plus 1, so on down. So Kayla says to us correctly that if I'm looking for the smallest set that contains any particular one of these, the answer is going to be A1. Notice that all these are subsets of A1. Everything underneath here is already contained in here. I don't want to toss in more things, so this will suffice to get us the union of all those sets. Does that need any more explanation at all? Let me know. Ashley, does that sound good? Sure, yeah, okay. I don't know you, so I'm not sure, I can't read your expressions, and I can't read anybody's expressions now. Okay. So now let's talk about the other side of this and look at the intersection. And this is where things get interesting. So we're looking for a set, the set of all things in common to all of these sets. As this is intersection. And you might want to look at this slowly. Right? So let's just take a look a little bit at a time. What would A1 intersect A2 be? What is in common to both those sets? A2, yeah? The smaller of the two, right? So when I'm looking to see what's in common here, and then when I come down and I go, all right, well, what about A1 intersect A2 intersect A3? What do you think, Kenny? Just A3. Awesome. What if I come down and then I say this? So let's make a bold leap. A1 intersect A2 intersect A sub n. And here, n is going to be a number bigger than 1 for this to make much sense. What would that look like? Yeah, could you, Noah, could you just explain a little bit? I agree with you.
So, A sub, every set that is lower than A sub n will start before A sub n and contain all higher positive numbers. A sub n will start at the highest point, which is n, and contain all higher numbers past that, as all other sets also contain. So they all contain A sub n.
Yeah, beautiful. Really nicely said. So is that making sense to everybody? That take a look at the set on the board and I say, what's in common with all of these? Clearly, you know, 1 can't be the thing that's in common with all of them. It's because it's only in A1. 2 cannot be the thing that's all in common because 2 stops being in these sets at this point. 3 stops being in these sets at this point. So as I move through, the intersection is going to be essentially the smallest set that I'm intersecting here. The smallest of these ones that I've worked my way up to. So absolutely, that's going to be A sub n. Yeah, is it good so far? But that's really not what this says at all. This says keep on cruising, go till the end of time. What is left that is common with all of these? Let me run to the restroom really quick, because I gotta go. And let me just give you a moment to ponder and maybe think of an argument justifying your answer. What do we think? Empty set. What's your reasoning on that? So let's see. So notice there's nothing in that set. Why is that?
Because if you try to put an element in it, if you try to put element B in it, then element B is not going to be an A sub B plus 1.
Damn, that's good. Yeah, that's great. That's the argument. That's perfect. So let's write that argument out and formalize it. So the problem is, as soon as you want to have something in this set, you realize that it just keeps slipping away, right? It's just always moving to the right. So as soon as you try to grab some element, let's just use B, just like Noah said. So B is a whole number. When will B be in the set? Well, it's going to be in A1. Let's say B is bigger than 1. It's going to be in A1 because this has everything. Maybe it's going to be in A2 if it's bigger than 2. But eventually what's going to happen is I'm going to get to set A sub B plus 1. And it's going to be to the right of this thing. And it's only going to contain stuff that's bigger, natural numbers bigger than B. So this cannot be in that set. And let's write this out. Notice that for any natural number, and I'm gonna go with a more traditional, less exciting letter. Sorry. So for any natural number M, we know that M is not an element of A sub M plus 1. For something to be in an intersection, it has to be in every single part of that set that composes, of which that intersection is composed. So if something's in here, it has to be in everybody. No matter who I pick, it will eventually not be in somebody. And it's going to be in none of the sets to the right of this, so it won't be in this. M is not an element of A, M plus 2, and I can just keep on cruising like that. So this M cannot be in the intersection. Intersection. Piece of M. Infinity. And thus this intersection must be empty, because the only thing in here are natural numbers. So since this intersection must be a subset of the naturals, and no natural is inside of it, we must conclude that this intersection is empty. At some point, notice here how I suppressed the indices. We know what the indices are. When it's clear what your indices are running from, because you've already set up the context, you can just let them drop, and everybody will follow what you're doing. Okay, so I said this is a primitive, vital example. The idea of an empty intersection because the sets are just slipping away. Here we have nested, infinitely nested sets. When you have infinitely nested sets, be on the lookout for this happening. I swear to God, it's going to happen like, maybe not every week, but every 2 weeks. In some form. All right, any questions at all on that vital piece of our toolkit? It's a conceptual tool. All right, cool. Oh, man, we have so much time. This is great. Next key result. Let's see what's here. The next key result is something that is in every analyst's bag right at the top, so you can always reach in and just grab this thing. It's at your ready. And that is the triangle inequality. Oh man, is this important. This shows up in almost every math class, I think, at some point, besides abstract algebra. Any place where you're measuring stuff, triangle inequality is going to be your friend. What do I mean by measuring? Well, absolute value. The absolute value function measures the distance from a real number to 0. Let's actually put that up here. So let's see, so the absolute value function. And we'll put a little dot in it like that, just denoting it. Well, hell, let's put a letter. Oh, I'm going to go with B. I like the B thing for today, so thanks. Yeah, that's cool. It's exciting to have a new letter to hang out with. Absolute value function B equals the distance from real number B to 0. And distance is always a non-negative quantity. So for example, if I have negative pi, 0, the absolute value of negative pi is pi, because that's this distance right here. So that's the kind of intuitive way to understand absolute value. I'm going to give you multiple definitions for absolute value. If we were doing calculus, if we were going to take derivatives or anything like that, this is a handy definition. So here's some alternate definitions. The absolute value of B can be computed by squaring B and then taking the positive square root of B. Now that you do this, you can take the derivative of it now. Has anybody ever seen that? Taking the derivative of the absolute value function? Let's do it. Yeah. For friends, for math friends. So if I have to take ddB, the absolute value of B. Now I don't want B to be 0, because it's not differentiable at 0. So let's just say B is not 0. That's okay. So this is equal to ddb of b squared to the 1/2 power, and then I chain rule that b's, right? 1/2 b squared. So, and then simplify the 2's to cancel. This turns into, so. Yeah. And this is the definition of absolute value. So the derivative of the absolute value is b over the absolute value. Let's plot it. Plotting things. You gotta plot things. You gotta love plotting things. If you're a math person. So notice that what this does is it takes like a number like 7 and divides it by the absolute value of 7. So it turns 7 into 1. It turns any positive number into 1. So if I take a look over here, I'm going to put an open circle right there. That's the output. It turns any negative number into -1, right? So -3 divided by 3 gives me -1. And so there is the graph of that function. You can always take a derivative of absolute value as long as you're not doing it at 0. So that's a fun one. Probably never use that in here. What we will use are one of the two next absolute value definitions. See, today you're already learning more about absolute value than you ever thought there was to know. So that's definition 1. We'll call that 1, 2, call this 3. The absolute value of b is equal to, and I can do it piecewise. If the thing inside here is not negative, I'll just return it. So if it's 0 or a positive number, just literally spit that back out. So that's if b is greater than or equal to 0. If this number in here is negative, like -5, I'll just negate it. So I'll spit out negative b if b is negative. That's a cool way. Here's another cool way. So that's 3, here's 4. The absolute value of b is the biggest of these two values. Take the number inside here and its opposite and pick the biggest one. That'll be the positive version. So this would be cool. This would be, nice for coding or something like that. You wouldn't need to write your own absolute value function. Those pretty much exist, but very algorithmic. That's all I got. That's my last definition of absolute value. But absolute value is a big friend of ours. So let's go back now to the triangle inequality. That's just like the preface right now. So the triangle inequality says the following, that if a and b are real numbers, then the following is true. A plus b, the absolute value of a plus b, is less than or equal to the absolute value of a plus the absolute value of b. So, let's prove that. A bunch of ways to prove this. I'm going to show you, let's see, I think I have 3 written in my notes. Let's do the fun. Let's do a nice fun definition of this. So, let's see, which way do I want to go? Yeah, so, proof. A proof. Go to, what's the computer place, Stack Exchange? Yeah, is that it? Yeah, go there and you can find like people just contributing proof after proof of this triangle inequality. But this is a nice one. So first off, let's just take the absolute value of a plus b and square it. sure I'm going to the right place. Yeah, so since I'm squaring it, it's literally just the same thing as if I added those two numbers and squared. Notice here, I'm adding, then squaring. Adding, taking absolute value, and squaring. Here I'm adding, and then squaring. Does this seem reasonable? Let me stop. Does that seem fair? That whether or not this quantity in here is positive or negative, if I take the absolute value and square it, I get the same thing as if I just square it anyway, right? So for example, if I had the absolute value, this turned out to be -3 inside here. That's the same thing as 3 squared. But it's also the same thing as -3 squared. You really get the same answer no matter what. Whether or not there's a minus in front of this doesn't really matter. So now the magic comes from FOIL. We know this. We don't know anything else. We know this. Fact, I'm going to put a question mark here, and I'm going to ask you to explain it. If I have a real number x, is that true or false? Yeah, why do you say yes, Kayla? I agree.
In the event that x is positive, then the absolute value of x will be equal to x. But if x is negative, then the absolute value will be greater than
Yeah,
x.
beautiful. Yeah, exactly. And it actually, it follows nicely from this definition right here. X is less than or equal to the max of these two quantities. Surely. And this is literally the definitions. Here's a little proof right here, a mini proof. So that means I can take each one of these quantities and bound them above by their absolute value. B is less than or equal to its absolute value. A is less than or equal to its absolute value. Sound reasonable? Stop, go slow, sip tea. And then this, can anybody tell me what I could do with that right-hand side?
Word for it.
What can we do with that right-hand side? Could we factor it? Yeah, what does it factor as?
The absolute value of a plus the absolute value of b squared.
Beautiful, yeah. Foil this out, you get that, right? Yeah. So now look what we have. We have the absolute value of a plus b quantity squared equal, less than or equal to this. So let's summary. So in summary, we have this. How do I get the triangle inequality? How can we get the triangle inequality? Take square root. Square root is an increasing function. So if two things that you are taking the square root of have an order relationship, the square root preserves that. So take square root, positive square root, and we get the triangle inequality. That's one proof. That's my favorite proof of it, I think. Really. Whew. Boy, these N95s are not comfortable. That is not feeling good. Let's try that weird setup there. Weird. Okay. How do you guys keep these like do your ears hurt? Okay, so my ears will just hurt. Good, nice. Okay, all right, good, great. Any questions on that, my friends? You don't need to know the proof. It's not going to be on an exam or anything. What you do need to know is that this is going to come come up all the time. And you have that result at you ready. Okay, so let's take a look at a consequence of the triangle inequality that includes an incredibly common trick. So, common trick using the triangle inequality. Let's see. Okay, yeah. So let's take the quantity A minus B. Now the trick is what I'm about to do. I'm going to insert 0 as a plus and a minus at the same quantity. This is a massive math trick. It happens in every little sub-discipline of math. So notice here that I'm going to rewrite this as A, let's see, do we want to go, yeah, A minus C plus C minus B. And I want to write the triangle inequality in a way that I think is good for your brain. The triangle inequality isn't just about numbers, it's about quantities. And really it says that if I have some quantity plus another quantity, they are less than or equal to the sum of the magnitudes of those quantities. So sometimes you'll want to group together a collection of symbols and treat them as a single entity. And that's really what I'm going to do here with those two quantities. So this is less than or equal to the magnitude of A minus C plus the magnitude of C minus B. And notice that this is true for any 3 real numbers. So this trick is something you'll do regularly. And it'll involve the triangle inequality. Most certainly. We are getting through good stuff. Now we're getting to the real nitty-gritty. So let me stop and let you take a breather and just see if is there any questions. Are we good? Good, good, good. All right. Okay. So, last pivotal result, and I would almost say I don't want to put anyone on a pedestal, any of these results. But if I could crown one of these results for analysis, it would be Theorem 126. Just what makes real analysis go down. And it also is kind of like one of the things that makes you either like real analysis or hate real analysis. And if this result upsets you, you should become an algebraist. Right? This is right now. This is the test. This is the litmus test right now. So this is Theorem 126. And it is, let's crown it. You can gender our ruler as you see fit. It is our ruler. So let's see. It just says simply this. 2 real numbers, A and B, are equal if and only if the absolute value of A minus B is less than epsilon for all positive epsilon. Okay, stop. Read that through. Take a second to bring that into your awareness. Prove it. But let's what does it say? that two quantities are equal if the magnitude of their difference can be made as small as we want. I'm going to write that out. So A and B, not B, so I spelled B. B are equal if, and maybe you can put an if and only if there, what the hell, why not? If and only if we can make the magnitude of their difference and watch, I'm going to say this even differently than I just said it, arbitrarily small. As small as we want. We are almost never going to literally work with equations where you've got this equals this, and this equals this, and you work through a string of computations to show something is equal to something else. We'll almost never do that. I can't even think of a time we'll do that. Rather, what we will do to show that something is equal to something else, to prove this, we will demonstrate that no matter how small this number is over here, we can make this a true statement. That's how analysis works. So let's prove it. Now it's an if and only if. So we've got two things to prove, right? That's biconditional. Let's do a nice formal proof. We need to demonstrate two things. First is that A equals B implies this. And then if I can make this arbitrarily small, if this for all, put in a for all here, that implies that A equals B. Which of these two is the low-hanging fruit? Let me let you think about it for a second. If you were to prove this and you're under duress, you're in some Jigsaw movie or something like that. Jigsaw is.
Want to do computational analysis.
That's it. Yeah, exactly. Or some goofy Batman villain that's hanging you over a pit of acid. You have to solve this to get out of it. Which one do you go with first? Yeah, why is that, Noah?
Just because then I start with an equals instead of a.
Okay, I like it, because it just feels safer.
Yeah.
More homey.
Exactly.
Yeah, it's like closer to the heart. Okay, I like that. Cool. All right, so to show, let's call them 1 and 2, so we don't have to rewrite it. To show 1, assume A equals B. That's nice. That does feel good, doesn't it? An anchor. Then, well, let's see, what do we got to show? So we need to show that right-hand side. So what does this become? 0. And surely, given an epsilon that is positive, that epsilon has to be bigger than 0. That's literally the definition of being a positive epsilon. So this is less than epsilon if epsilon is greater than 0. I'm just flipping it. Right? So it's almost so obvious that it's kind of confusing. Does that make sense? If A equals B, this is dead. and it's less than any positive quantity. So that's the easy direction. So good call on that, Noah, you know. Work with always go for low-hanging fruit first. Let's start with 2 now. To show 2, we need to show this implication here. Now, I'm going to suggest that we try a proof by contradiction on this one. So let's proceed. We can either do contrapositive or contradiction. Let's go with contradiction. So proceed with proof by contradiction. Ooh, let's remind ourselves of what that means. So proof by contradiction. So essentially, we're going to, we want to show that something implies something else. Here, I want to show that this implies this. So how does this work? Can anybody help me out here? What do I do to do a proof by contradiction?
Well, there are 2 ways. You can start with like the original assumption and then show that it does not create, or it does not lead to the like product that you were looking for, or you can start with a faulty presumption and then show that it gives you what you're looking for. So that neither way are you showing that it's correct.
Yeah. That sounds real good, Kayla. Absolutely. So what we're going to assume is that this is true, but this isn't, and show that that can't be the case. So, because right now, let's actually just go back just a little bit more to make sure we're on the same page. This is essentially implication is a light switch hooked up to a lamp. And oh boy. So here's a bulb, something, this is like a light. And this is the thing that's in the box. And then that's the light over there. So when I say that this is true, what that means is that this being true engages this. So if I flip this switch, aka make this true, it turns on the light. Now the thing about implication is you don't know if there's other switches, right? So potentially there are other routes to turning on that light. So just because that light is on doesn't mean this switch is on. But man, if that switch is on, that light better be on. So proof by contradiction says, okay, wait a minute. Let's assume that this switch is open. Oh wait, let's see, wait. The switch is on, but the light is off. That's proof by contradiction, where I close this switch and say, the light didn't come on. What's wrong? How could that possibly happen? So that's what proof by contradiction, in theory, is doing for us. So proof by contradiction says we're going to assume that this is true, but A minus B, or A is not equal to B. Something's going to go haywire. Something's going to explode. All right, so if A is not equal to B, what could I say about A minus B?
It's greater than 1.
Wait, say that again? Sorry.
A minus B is greater than 1, or
Does it necessarily have to be, because like here I could have
or
like
is greater than 0.
0.1 and 0.2, those aren't equal, but their difference isn't bigger than 1.
So it just doesn't equal 0.
Doesn't equal 0. Yeah, exactly. So you could literally think of subtracting B from both sides here, right? And then that would get you there. Yeah, exactly. Thank you. So we know that this is not equal to 0. So its distance from 0 is also non-zero. And in fact, this is a positive quantity when I take the absolute value. So i.e. absolute value of A minus B equals some quantity epsilon sub 0 that is positive. Where's the contradiction? It's in front of us. Where's the contradiction?
We assumed that A minus B was less than epsilon.
Than any epsilon, right? Yeah, exactly. So we assumed that no matter what this quantity is over here, absolute value of A minus B is less than it. No matter what it is, this is less than it. But now I've just found an epsilon naught that contradicts that. So here, this means that A minus B absolute value is not less than that epsilon naught. It's freaking equal to it. And so this is the contradiction, which contradicts the assumption that regardless, and I'm going to write this out so that you have it nicely in your notes, because it's subtle, that regardless of epsilon greater than or equal to 0, we have this. Thus, let's see, what caused the problem? Thus, A must be equal to B. A must equal B. Because if A is not equal to B, there's a distance between them. All right, let's actually think about that. Just drawing a picture on it. If here's A and here's B and they're not equal, there's some distance between them. A fixed distance. And that is that epsilon naught that I'm talking about. Another way to say this is two different real numbers have a positive distance between them. Now, you might think that's pretty obvious. Two different things always should have a positive distance between them. That is not actually true. There are places in math, strange spaces, where things can be different, but there's no distance between them. And that's a weird ass thing. We don't, you go to grad school. that's like way off in the yonder, or the glow over the horizon. You got to do some weird stuff to make that happen. It's not something you would encounter in just normal life. All right, so in case we had extra time, I had a little fun problem for us. I'll put it up on the board. This is just like for us to have fun because we come here to play. Right? You're in math because you like playing. You like these games. So I'm just gonna put this on the board. Feel free to work on it. So gaming. Show. And I will tell you that the tip was somewhere in today's lecture on how to solve this. To show that the geometric mean of two numbers, so let's say x and y are both positive numbers. This is the geometric mean. You multiply them, then you take the square root, is less than or equal to the arithmetic mean, the average, for any two positive real numbers. Let's see what time we got. We got like 4 minutes. Just take 4 minutes. Let's do math, constant, forever.
Bye, recording watch.